everyone. Welcome to one of the last sessions of the day. We'll jump ahead. Today, we're going to talk about designing, building, and testing an OCP AI cloud network with industry-leading performance. So my name is Matt Roman. I'm joined by J.M. Hands from FarmGPU and Mark Austin from Hedgehog. And we'll give those guys a sec to introduce themselves in just a minute. There we go. Let me just give you just a quick intro for myself. So I lead product marketing and technical marketing for Celestica's platform division. For those that don't know, Celestica is a large technology company headquartered up in Toronto, Canada. Large, about $10 billion in revenue. We do a lot of different things, but pertinent to the discussion today, we design, manufacture, and bring to market products to our hyperscale customers, to OEM customers, and we bring products to market under a Celestica brand through channel partners and direct to end users. And we wrap a service and support offering around that. So that's a bit about what we do. We'll talk a little bit more about some of the Celestica products that are part of this solution. So that's it. Jim?
Yeah, and John Michael Hands, CEO of FarmGPU. So we're an AI neo cloud specializing in on-demand GPU compute. We actually use Celestica and Hedgehog for our B200 cluster build and learned a lot along the way, which is what we're going to talk about today.
Yep. And I'm Mark Austin. I'm founder and CEO of Hedgehog. We do the AI network software for the Celestica network hardware that you're using.
Very good. Thanks, guys. So just the setup for the presentation today, it's really in three portions: design, build, and test. And we'll kind of hear about kind of some things that went really well and what some of the challenges were and what things look like moving forward. So we'll jump right in. I'll just quickly touch on kind of the main Celestica portion of this discussion. And that's our 50 terabit switch platform. It's called the DS5000. It's based on a Tomahawk 5. It's a super dense, high performing system that runs the Sonic network operating system. And the platform itself, in the spirit of openness, it is an OCP accepted design. So that's the DS5000. Next,
hey, Matt,
Mark.
you might actually want to talk about Open Compute projects. So, because we're at the Open Network Users Group conference, but probably some people don't know what OCP is.
Yeah, so OCP is Open Compute Project. It was originally started by Meta back when they were Facebook, and it was really an open source, open standards effort that covers many different parts of, I'll say, the IT stack, whether that's data center. Originally, that's where the Sonic software stack started. It covers everything from cooling distribution units to chiplet technologies to lots of different things. So it's a really large industry group driven by large network operators. There's vendor participation, research, academia. So it's a really big group. We just had the OCP Global Summit last week out in San Jose. I think there were 10,000 plus people that attended. But for us, it's really important. Celestica has been pretty active in a couple of different things. We've contributed designs, networking primarily designs that have been accepted, and there's a couple of different levels of contribution, but the most detailed level is we contribute the whole design, schematic files, Gerbers, bills of materials, block diagrams, specs, all those sorts of things, and that's available to the public if you just go to OCP. And we've contributed 3 or 4 other platforms as well, everything from a low-end management switch all the way up through edge gateway, SASE type platforms, and then the largest is the DS5000 platform. And we actually just, shameless vendor plug, just announced our DS6000 100 terabit switch platform that will find its way into OCP as well.
And it's safe to say that when you're doing an OCP design, there's a hyperscaler involved typically. And so you're designing for hyperscale, and then now we're making it available to neoclouds and enterprises. Yeah,
that's the tagline I love that Mark says. That's part of Hedgehog is network like a hyperscaler, and regular enterprises can get access to technologies and methodologies that power the world's largest and most complex, cloud-based networks.
Great.
All right. Mark, you want to?
So we're talking about an OCP, an Open Compute Project reference architecture. So Matt just talked about the OCP hardware. Hedgehog is OCP software. So we've got a Sonic showcase here at ONUG. Sonic started as an open compute project, and then kind of administration of that transferred to the Linux Foundation. So Hedgehog is a Linux Foundation member. We're a Cloud Native Computing Foundation member. We build on that Sonic project with Hedgehog, which is an open source software appliance that has all of the OSS components you need to be able to run an AI network at scale. And the Hedgehog project it's a project in CNCF, and it's designed from the ground up to work with other CNCF projects, so that you can operate your own AI cloud with the same people, same process, same tools, same skills that you already have with CNCF and cloud operations.
Thanks, Mark.
Yeah, this is one thing we had from the OCP Global Summit. So the two OCP components that we use as part of our data center stack are OCP NVMe SSDs, and there's a lot of functionality that we have as far as like predictive health monitoring and telemetry and AI debug that the extended log pages that Microsoft and Meta have put into these drives. Actually, we can use too, which is again part of the good thing about OCP is that you can just the spec that was written by Meta and Microsoft is open source on OCP contributions. You can go look at all the good stuff that's in the log pages, but we have these, and turns out we have the highest storage performing B200 clusters in any portfolio for any cloud vendor. We have 8 PS1010 PCIe Gen 5s over 100 gigabytes a second local to each node, which is very important. And then we have network storage that we use actually the DS5000 for, which is some of the other things we'll go into. But I think the next slide.
And
is,
just that's not by accident. You have some experience in storage, right?
Sure. Yeah. It's we have another longtime Intel guy in the audience here, but I was at Intel for 10 years, but before I left was running the product line management for all the data center NVMe SSDs. And so these guys back when I was at Intel were all my customers. Now I get to be a customer and use the drives, which is a fun thing to flip that around. Well, one of the things we mentioned, we're doing on-demand compute. And when somebody rents a cluster, they expect really good performance. They're paying extremely top dollar for these GPUs. And when they rent them, they're basically reserving that entire instance. So the product that we were building this backend fabric around that we ended up using Celestica and Hedgehog. So one was we selected OCP style gear because of all the things that I just mentioned. We like OCP because it's open. I can just go download the specs. We can write custom code if we need to. There's no vendor lock-in, and we just like everything open. And so anytime we have an opportunity to use OCP gear, these were going into a standard data center, not like OCP open rack V3s and custom multi-100 kilowatt designs. These are just going into a standard telco air-cooled rack, and we were able to do 2 B200s per rack. And so we basically designed this system around a product called RunPod Instant Clusters. So RunPod is one of our partners for the on-demand platforms, where somebody can rent the entire cluster with their Docker stack in one click and be able to run MPI and Slurm to actually do a training run across every node in the cluster at full bandwidth. Well, to do that, turns out with Ethernet is actually pretty tricky. There's a lot of stuff that we had to go figure out with RDMA and performance and tuning to benchmark the cluster. So I think what we're going to talk about today was some of the design goals, but then all that lessons we learned along the way while we're trying to build this cluster.
The good, the bad, and the ugly.
So, initially, like when we're talking to investors about building clusters, typically there might be like a 90-day bring up or something like that to get to your maximum occupancy rate. And when investors are investing money into a cluster, they expect that you're delivering revenue on these like immediately as fast as you possibly can. It ended up taking us like about 3 weeks total to get this cluster up. And one day was spent racking and getting the BMC and updated and basically getting the NVIDIA drivers installed and doing the basic bring up. We actually found 2 NVIDIA bugs during that bring up. There was a bug with Ubuntu 24 and CUDA, which prevented all CUDA from working. We had to do a software workaround. And this was like a known issue at the time. Blackwell was like really new. Like Blackwell was very, very new when we did this cluster. And there were some bugs that we encountered. But 3 days into the cluster, we already had the full burn-in test completed, all the NVIDIA diagnostic tests working on the cluster. We're like, great. Let's start working on the back end. So turns out most of the pain in this bring up was on the network. Like, 3 weeks of the 17-day, whatever total cluster build time was spent in network debug. And one of the things was, look, when we went to go order optics, they're like, oh, well, there's some optics that are compatible, but those are 6-month lead time. We're like, that's great. We're not delaying this cluster for 6 months. So just give me any ones that you possibly can. So we go to plug these in, and we found like there was a bug with it ended up being like one of these things where is it the optic, is it the switch silicon, is it the software, is it Sonic, and everybody's kind of pointing at each other.
They wouldn't power on at first, right? You weren't getting light, right?
Yeah. So we there was like all kinds of different. So it turns out there was a really nasty bug that if you had the port broken out on the switch in Sonic before you inserted the optic, that it wouldn't actually finish the initialization sequence. And it was really hard to track down because you'll see we had a bunch of other bugs during this process, but the workaround was to hard power cycle the switch after you've already had the modules inserted. And when you're debugging stuff, people are like pulling modules out, putting them back in. Let's try another module. Let's try this one. And people are just swapping. Like, this was a really, really nasty bug. And so one of the things that I was really impressed with was the ability for all these guys to get together basically on like a Saturday afternoon and like just grind through like a 10-hour debug session with and we had like the optic guy come fly to our data center to like go figure this out. So yeah, it was really nasty. We had this was like a small, like we started with 6 nodes and we're expanding to the full 32 nodes in this cluster. And for the 6 nodes, I'm like, oh, well, I'll just have my team do the fiber optic cabling. They've done some fiber stuff, but never 800 gig. Well, yeah, they made some mistakes. Like the technician used like a breakout cable that was supposed to be like an MPO12 for the 400 gig. There was one time where the technician had like a cut sheet for the serial numbers on all the cabling, and the optics on the bottom of the DS5000 are like inverted because so port 1 and port 2 are backwards because the optics on the bottom. Like the tech didn't know that, right? He just like, it's port 1, port 2, like, and so remotely kind of debugging this stuff was challenging. So there were cabling issues. There was a dust issue we had to clean, and turns out, as you'll see on the next slide, the next one's probably a good one. Like, there's like a lot of stuff that can go wrong in the physical layer, and we hit every single one, like optics issues, cabling issues, switch compatibility issues. And one of the big lessons learned was, obviously in a perfect world, we would have had like months ahead of time to be able to plug in all these optics and test them out with all the different configurations. But we didn't have that. We had to do it on the fly because that's when we got them. The other thing, so just to get the link up, you don't just plug these things in. We had to like turn auto negotiation off on the switch side. We had to turn it off on the ConnectX-7 side. And so it turns out when you change something like this, when we got the ConnectX-7s, they were in InfiniBand mode, so we had to turn them to Ethernet mode. This should just be like an easy NIC reset, right? Oh, great. Well, we need reset the NIC, and there's an issue where it just resets the entire Supermicro server. Oh, well, there's a bug that we filed with Supermicro where the server just randomly hangs like 1 out of every 20 reboots for like hours. And so we're sitting here on the call with like 20 people debugging, and we're like, oh, just reboot the server. I'm like, guys, I think it's hung. We're going to have to come back in an hour. I'm sorry. So there's just random stuff like that. But like I learned a whole lot about the Mellanox tools like MLX Link and MLX Config but we had to basically hard code the link speed to get these to link up with the the DS5000. So the good thing is now is we have a playbook. We've actually Ansiblized every single thing in this list to where when we build a new cluster, we run the playbooks and it goes through all the stuff that we learned to check every single thing. Now, I mentioned when the whole point of building this super high-end back-end fabric is so that all the GPUs in the cluster can talk to all the other GPUs at full bandwidth. And so on the B200s, they basically have 2 NVLink switches on board in the B200s, so all the GPUs can talk to each other at 1.8 terabytes a second within the node, and that runs sort of like InfiniBand style networking between on the NVLink switch. That's all managed by NVIDIA Fabric Manager. If you have InfiniBand, now the Fabric Manager also manages your connection outside the nodes. Well, if you have RDMA and Ethernet, that's not true. You have to give the ports IPs, you have to give them subnets, you have to look at the interface names. So a bunch of debugging was trying to figure out, okay, like, is the Mellanox Ethernet config name, is it always going to be the same on every server in the same slot? Is it going to be, we have to make sure they're all on the same subnet, on the same rails, so they can talk to the different GPUs and the different server. When you're talking about cluster level performance, well, the gold standard for understanding cluster level performance is NVIDIA Nickel test. So there's basically an all reduce where all the GPUs and talk to all the other GPUs in the cluster, and you can basically look at the bus bandwidth or average bus bandwidth for different message sizes, which basically is saying how fast can each of these nodes communicate to each other. So to get that number really high, you have to have, if one of these things in this list is wrong, it will not work. And meaning like the BIOS changes. If those two things are not enabled, so PCIe ACS, if that's not enabled, well, the NICs are not communicating with the CPUs. The NICs are communicating to the GPUs, and the GPUs are on a PCIe switch with the NICs. If you have ACS enabled, then it goes to the CPU memory as a hop, and then back to the switch, and then back out the Connect X7. That's really bad. You've just halved your bandwidth with one BIOS setting. And so turns out you just turn this off and you 2x your performance. And so there's other ones where you have to disable IOMMU. So if you're renting like us, we have like clusters that we rent out with KVM VMs, like, and now you have to like make a trade-off. Do we make this cluster better for training performance, or do we like use KVM VMs? That's like a pretty big trade-off. So there's stuff that you have to work around there. The drivers I mentioned, oh my gosh, NVIDIA driver documentation is not so good. So like getting all the nodes to have like the right version of the Mellanox OFED drivers and that enabled the RDMA devices and had consistent naming across this, like that took a lot of pain to get there.
So in sum, it's hard.
Yeah.
It's not easy. And there's a lot more to an AI network than just the switch, right?
Of course. Yeah. And the switch is just one thing, right? And when you're looking at what are we building these networks for? We're building them to train AI to train AI models, right? And to train the AI models, they have to have this super high speed bandwidth between all the nodes. It's a nickel. Again, one of the cool things we announced at OCP is that with all this pain and learnings that we learned with building this cluster, we're just going to put into an OCP reference design in a white paper. And kind of open source all this learning so that the next person that goes and builds a cluster like this, that they'll have all that learning with us. This nickel test is very, very challenging to run. Like the documentation also not so good, and there was a lot of tribal knowledge that we had to get passed on to us. Thankfully, Semi-Analysis, who was benchmarking our cluster for their upcoming Cluster Max V2 benchmarks, gave us some nice hints on some of the things to do. Like, basically said that what makes this workload extremely challenging to run is to run it properly. You need 4 HEX nodes. You're basically 4 servers that have 8 GPUs in them to properly run this benchmark. If you have 2, there's some tricks on the all reduce that basically make it so it's more bandwidth than you'd actually expect in the real world. So now the other thing is that when you're comparing performance, as the cluster size increases, the lower message sizes are going to suffer. And so it is challenging to figure out like, and one of the other things we learned was like on a B200, it does the first step of the all reduce inside and then transfers the data over. Well, it's super fast on a B200 because they have NVLink V5 switches. So this was a very, very challenging benchmark to run, and it took us weeks to go.
Yeah, just doing the benchmark testing is not easy. So
can you comment just how important those benchmark tests are for your business?
Yeah, yeah, and that's sort of nice cue into this next slide, which is.
Before we go there, though, I want to talk about how we're going to make it better next time, right? Because first off, it shouldn't take you 17 days to bring up a fully automated Hedgehog Celestica AI network. It should take you 1 day, right? After everything's cabled, it should take you an afternoon, right? So our job, Matt, your job, my job, is to make sure that your next deployment, which is going to be 5x the size, right, is a lot smoother. And so that starts with certified optics. You want to talk about a little bit about that?
Yeah, and I think that's and you hit a few key points, and we've had many engagements with customers that just go source optics, and everyone thinks that because the form factor is standardized or that there's an MSA, that it's just plug and play and it just works. And I think many of the people here, recognize there are hundreds and hundreds of pluggable optics vendors, and a lot of household names, a lot of suppliers in China that are just kind of reassembling. But and for a single port low speed pluggable, probably not that big of a deal. But when you're talking about 400 gig, 800 gig, 1.6 coming, all of these various breakout modes, there's a lot of complexity and gearboxes, and so that optical piece can be really complicated. And frankly, Celestica, we have a validated set of pluggable connectivity, and we make a significant investment to test when we release products, and then to do continuous testing every time we do new sonic releases, new firmware, new BIOS. All of that needs to be revalidated. So
Yeah.
that connectivity piece is, a lot of people don't realize how much complexity there is.
There's
there.
two ends to the link.
Right, and that's the other piece. What are you connecting
Yeah,
to?
and there's a few components that make up the link. Yeah, and it's test and retest, right? So part of our job at Hedgehog is to take your hardware, certify it so that it works well with Hedgehog software, so that your solution's fully automated and zero touch provisions. So that means that, you know, our hardware certification list needs to include the same kind of certified optics, the same continuous automated testing, and then all the stuff that JM described about managing the host end of the link, right? We need to automate that too, right? We need to be you know, productizing all of the configuration, all of the driver updates, all the stuff that JM described, so that that's part of the ZTP along with the switch. And so that's one of the things that we committed to doing, not just for you, but for the OCP community.
That's awesome. All right, in the last couple of minutes, you want to talk about testing?
This is
and
the good
performance?
stuff.
Yeah.
Yeah.
You know, so we went from basically not knowing how to run this benchmark to, after 2 weeks, they're like, I think we have the highest RDMA score ever recorded, potentially.
Pretty cool.
You know, the new Cluster Max V2 is coming out here in a few weeks, and you know, there's going to be new ConnectX-8s with 800 gig in the mix, and there's GB300s that are already, like, there's all kind of crazy stuff. But as of right now, this was the you know, kind of, we're comparing our results on the B200 cluster versus what they had in the Rev 1. And I was really impressed. We kind of graphed all this out. I was like, okay, are we finally doing good? And after we put this in the graph, I'm like, man, we killed it. And so I mentioned a lot of stuff, especially around the RDMA tuning and making sure all the message sizes are correct and you have the right RDMA tag and all this stuff in the benchmark that we had to tune and tweak. And you have to compile your own version of this test and run it. And but again, semi-analysis basically, to get the highest model flops utilization on your cluster, if there's any drop in network performance, your GPU utilization will suffer tremendously. So it is not like a nice to have. You have to, like, the communication between GPU nodes is absolutely critical in training big AI.
And if you don't get that, you're not gonna rent the GPUs, because your customers are gonna go elsewhere where they get higher performance compute, right?
And I'm really excited. I mentioned that, you know, this enabled us to launch this product where a customer can spin up an entire cluster with full 800 gig backend fabric in just a few seconds, and have them already all pre-linked together, and basically Slurm and MPI install where they can start a training run immediately. And the magic of this instant clusters is when they're done with it, they shut it down and it's all run through Docker. Everything's cleaned up automatically. The next customer can
So it's multi-tenant.
Yeah. So this is like a very, very clean and beautiful solution. And it's actually much, like, the customers like it a lot better than Kubernetes. So we're excited. This cluster has basically been rented out since we launched it. And so if you want to rent it, too bad. Sorry, it's already rented. But
You're building
you know,
more.
we're gonna buy more.
I kind of want to, like, dig in on these bars, because if you should look at the chart here, right? So sweet spot for most AI workloads between 32 and 256 on the message size. The blue chart is your network, the blue bar, right?
Yes, I should note that so in each of these nodes, they have 8 ConnectX-7s that are 400 gigabits per second. And so if you do 8 times 400 gigabits per second, you get, you know, 400 gigabytes per second. And so we're able to achieve 392 gigabytes per second, almost near perfect scaling on the bus bandwidth at high message size, which is like we thought the numbers were wrong when we first got it, but there's no way it can get that close to, like, the theoretical. But so I was very excited, but that is the theoretical limit of the 8 ConnectX-7s. So again, because all the GPUs can talk to all the GPUs in their own node very fast, but when they have to go outside the node, now they use RDMA over Ethernet over the 8 ConnectX-7s.
And the other bars are other sites that semi-analysis is tested with the same nickel tests, right?
Yeah. Yeah, and there's some interesting thing. Obviously, NVIDIA talks about, you know, Sharp playing a major role in the XDR switches, where they actually do a step of the all reduce in the actual switch, and some tricks that they can play. But at the end of the day, you know, Ethernet is the scalable and lowest TCO. And so, you know, why we picked Ethernet was because it was cheaper than the other thing. But it turns out that we had a kind of an intuition, like, we think we can make this work on the performance side, obviously, and we're assured by our partners here that it would be great. And I'm glad that ended up working out.
Me too. Yeah, I mean, look, I think like, this is newsworthy. If hopefully everyone in the audience is getting this, like, nobody's ever done this before. It's pretty cool.
Yeah, and a bunch of people walked up to us after the OCP presentation about like, oh my God, thank you for being honest. Everybody's just talking about, oh, we're building a gigawatt cluster here and doing this, and like, it's like, no, you aren't. One and two, and like this stuff is really hard. It's really, really, really hard. And anywhere we can help along the way, because again, we're making money by selling this cluster. We're happy to pay it forward and have anytime we can use OCP designs and share it with the community. It's good. So.
Fantastic. All right. I think we are out of time. Thank you, JM. Thank you, Mark.
Thanks, guys. Thanks, Jam.
Great session.
Thanks, guys.
Thanks.